Okay, I think we're ready to start our next session here. Folks in the room and those online. Let me prepare for this real quickly and give an introduction. Okay, so our next speaker is Dr. Qunying Huang, and Dr. Huang is Associate Professor in the Department of Geography at the University of Wisconsin-Madison, leading the Spatial Computing and Data Mining Lab. Her research focuses on spatial temporal big data analytics, GeoAI, spatial networks, remote sensing, and image processing, with a primary emphasis on natural hazards and human mobility. She has published over 100 articles and edited 7 books. And please join me in welcoming Dr. Huang. Okay, Qunying, you should be able to share your slides and we'll be all set. And this session goes from 11:20 till 11:45.
Hello, everyone. Can you see my slides?
Yes, we can see it. Looks good.
Okay, thanks, Dr. Godfrey, for the great introduction. I'm Qunying, and so excited to be part of this event celebrating GIS days. As a geographer with a research interest in GIS science, today I will be here introduce the research work in our lab doing GeoAI and big sensor data for disaster response. In particular, during natural hazard, we have 2 types of data sets, big sensor data sets from physical sensing as well as social sensing, bringing exciting opportunities, yet come with also challenges. So in this talk, I will briefly introduce several case studies model developed in our lab, hopefully to give you some general idea how to tackling those big sensor data with the machine learning and the GeoAI approach. If there is time, I will briefly discuss the advancements I witnessed in this field. First, to get started, let me briefly introduce the physical and the social sensing data sets. First, in the physical part, we have sensors on board on satellites, UAVs, cameras, smart cards that can actively collect bigger data streams. Next, we have a social sensing data set from a social media platform such as Twitter, Flickr, Weibo, Facebook, Wikipedia, and YouTube, where each citizen or users are acting like a sensor contributing to data collection. In my work, I utilize both types of sensor data sets. And here I will introduce several case studies in this area. I will particularly utilize flood mapping to illustrate the potential challenges while utilizing remote sensing images for disaster mapping and damage assessment while they across different application, but the challenge for remote sensing image analysis and the interpretation are quite similar. The first one is heterogeneous image background come from the complex urban structure and the landscapes produce tremendous noise information in the remote sensing image. Second, flood water may show highly different pixel values. For example, here, the pixels in red circles and the blue circles are all flood water, but here you can see they show highly different pixel values, raise brand challenge to differentiate and subsequent for image classification segmentation tasks. Second, if we rely on traditional machine learning approach, handcraft feature engineering is a requirement. For flood mapping, we typically rely on the spectral indexes such as normalized difference water index, modified normalized water index, since the flood pixels are highly sensitive to green band as well as the near infrared band. However, such approach often produce model of low performance due to, as we mentioned earlier, due to noise and shadows cast on the remote sensing image from a complex urban land structure. Also, it is quite difficult to capture the detailed texture and the age structure information through handcrafted feature engineering approach. While recent deep learning-based model that can address the requirement of handcrafted feature engineering, however, it often requires a large number of human labels to produce a model with decent accuracy. In our task, we find it's often very challenging, time-consuming to produce the labels. For example, in our case, it takes even more than 3 hours for a domain expert to generate flood mapping mask or labels to indicate the potential flooding areas to inform our models. Not even talking about the millions of such labels are required to produce high-performance models. The last one is poor model generalizability and or transferability. For example, if our model trained with historical events like Harvey, Texas area, and it often cannot generalize, transfer applicable well to a different location or different events, such as Florence, North Carolina area. Facing all those challenges, our lab have done a series of attempts to develop the model, trying to minimize the requirement of training samples. The first one is we develop a patch similarity convolutional neural network, which we divide pre and post image into patches and classify each patch as flooded or non-flooded by calculating the similarity of pre-flood image and the post-flood image patches. It's intuitively, the more similar, the less likely it flooded, right? For the case study, we utilize 2 hurricane events, including Harvey in Houston, Texas area, as well as the Florence in Lumberton, North Carolina area. The data sets we utilize is planet scope satellite data sets with a spatial of 3 meter by 3 meter resolution. For both case studies, in the research result indicate that our model can achieve high performance with an overall accuracy more than 93% across both case studies. Further evaluation with different training samples indicate our model is able to perform urban flood mapping with only a few human labels. What we're talking about is 500 labels that can be complete in 3 minutes to generate, and it only takes 15 minutes to train our model, 1 minute to perform the prediction and the subsequent mapping task. Taking this achievement, we further develop a new solution that remove the requirement of training sample, even though we only include a few training sample. And however, it still require the effort, like 30 minutes to complete the labels. As such, we develop an autoencoder architecture through a self-learning framework that require no human annotation for model training. In the encoding process, in our model, we also develop 2 subsequent post-processing strategies, including spectral filtering and spatial filtering, to remove potential noise or false alarms based on the patch change map or vector analysis in our modeling process, further enhance the model's performance. Further evaluation again indicate that our self-supervised learning model can achieve comparable performance compared to supervised learning with an overall accuracy of more than 95% across both Harvey and Florence events. Further evaluation indicate that high-resolution urban flood mapping is possible without human labels through our fully self-unsupervised model learning approach. In particular, our model includes only two simple branch convolutional neural network to process the pre and post image subsequently for patch analysis, vector analysis to identify potential changes, which is flooded area, right? And our model can achieve strong performance, good generalizability, while without the requirement of handcraft feature engineering and human labels. The entire framework can be performed in near real-time fashion. The next effort is we further enhance patch-wise flood mapping to pixel-wise flood mapping, which is more complex since it's potentially produce more errors or false alarm at the pixel-wise classification and image segmentation. The key idea of weakly supervised learning is how can we automatically generate weak labels. By weak labels, we mean those labels are not 100% accurate, but fortunately, they are large scale enough with the automatic generation algorithm, and therefore can has potential to train a model with a decent performance. So in our case, we leverage different type of sources, including spatial, temporal, and spectral. For spatial information features, we extract from flood hazard layer from FEMA, building footprints from Microsoft to identify location with high risk of flooding. Based on the pre-flood imagery, post-flood image, we can identify changed areas of flooding, which is the flooding area, potential flooding area. By analyzing the spectral information through the spectral clustering near infrared reflectance analysis, we also can identify initial water cluster. Fusing all those information together, we then can generate weak labels, followed by subsequent machine learning classification model development for flood mapping detection. With ground truth, the evaluation of our weak labels showed the promising of our architecture. In fact, 97% of weak labels are accurately identified. Further evaluation with the different machine learning models and the input features, such as spectral information along with DM information, as well as global testing of our model, indicate that our model utilize the flood events in the United States, 8 in total, to generate the weak labels, and then we apply this model weak labeled models to test location in global areas such as Australia, China, Germany, Sudan, and Argentina, indicate that our weakly informed supervision model can achieve global mapping capability without the human labels, no handcraft feature engineering requirement. Again, the entire process can be performed in near real-time processing fashion. In addition to flood, I'm also particularly interested in the wildfire natural hazard. We develop a different model to automatically detect burnt area based on remote sensing images. Recently, we developed a bitemporal UNet model with attention mechanism and well-designed loss function in the model architecture. the innovation of our model is that our model will be able to handle imbalanced training sample, where the dominated samples are non-burned pixels, right? And the burned pixels are minority pixels. The next benefit of our model is it is able to pay attention to boundary areas with a mix of burned and unburned pixels, where often those areas is harder to predict accurately. And the third, our model is able to applicable to locations with diverse geographic and environmental context, which means our model can achieve good generalizability, transferability across different locations. To test our model, we utilize Sentinel-2 Level 2A products with a spatial resolution of 20 meters by 20 meters. To evaluate the generalizability, transferability of our model, we utilize Chico, California wildfire to train our model, and additional 4 locations, including from different continents, to validate our model. Here is the entire workflow. First, start from the data preparation and the pre-processing, followed by the model training for burned area detection and the mapping. Finally, we perform a model evaluation with different algorithm model architecture, including the loss function design in the model, as well as different evaluation metrics like overall accuracy, precision, recall. In addition to disaster mapping, we also develop different models for post-disaster damage assessment. For example, one of the effort is develop a spatial temporal constructive representation learning to automatically learn the feature of a building damage with big unlabeled data. As such, given one remote sensing image with buildings or other physical infrastructure included, we can automatically classify such image into no damage, minor damage, major damage, and destroyed. The major task of this model is what we need to automatically select or sample training image pairs to let the model knows what is the difference features in the image pair to learn the representation of features. We have positive, which means the image pair are similar. And also we have a negative pair, which means they are different contexts indicate the potential change or the damage in between the image pair. So the innovation of our work is we leverage laws of geography to inform the sampling process. For example, geographic distant remote sensing images are likely different, right? So they are likely negative pairs. Temporally adjacent images are more related, therefore are positive pairs. Similarly, images with similar geographic context are more likely related, therefore positive pairs. Now, next, let me briefly introduce the social sensor datasets and the GeoAI for disaster response and the natural hazard. Similarly, there are major challenges for utilizing big sensor data. The first well-known challenge is 5 V's, from massive volume, velocity, which the massive image are generated dynamic. Variety comes with different formats and content such as text, photo, videos. Veracity create trust issues. The last V is most the dimension I'm particularly interested in, how to extract the useful information from a massive data set. In the context of disaster management, the useful information, we refer that as situational awareness information. Information such as damage, donation and offer, information source, resource request, caution, advice, fatality, injury, missing people are all information that is useful for disaster management. Unfortunately, based on our prior study, we noticed that only a small number of social media data are situation awareness relevant. For example, based on the analysis of Hurricane Sandy events, in fact, only 2%, 70% of information are related to Hurricane Sandy, and less than 1% of information that actually are situation awareness relevant that can contribute to the disaster management. In order to extract such precious situation awareness information, we typically rely on two steps. The first one is utilize simple natural language processing and keywords to remove non-disaster relevant information. For example, in the Hurricane Sandy event, we collected 1.7 million of geotagged trees. Utilize Hurricane Sandy relevant hashtags, we only get 38,000 of trees that are Hurricane Sandy relevant. The next step we can do is develop advanced natural language processing and machine learning models to classify those information into different categories and remove non-situation awareness information, as demonstrated in our early effort that we develop a traditional logistical regression model that automatically classify those messages into 42 categories of SA relevant information at a different stage of disaster management, including preparedness, response, impact, which is a particular types of response stage, and recovery, and other, which is means Hurricane Sandy relevant but not contribute to situation awareness. In a subsequent effort, we also develop a deep learning-based model to support cross-event classification and situational information extraction. By support cross-event, we mean that our model trained on historical data set, it is able to classify data generated from a future event. As such, if our model is trained on Sandy, it's able to classify the message generated from Harvey subsequently. And further, Irma is also possible. And we can also train based on Harvey datasets for Irma prediction. Our model gets the best performance when we integrate Sandy and Harvey datasets to produce the classification prediction for Irma event. In the next effort, that previous model all rely on text-based features, which have a series of issues due to time constraint. I will not discuss detail here. So subsequently, we develop a geographic context-aware text mining model to integrate geospatial and temporal features into the text mining classification, make it a GeoAI model. In particular, we utilize data sources from social networks, Earth observations, official data sources, and the physical simulation model to generate spatial features such as distance to the social media post when it was posted on the social media data sets, and also temporal features to further enhance our model significantly. In addition to text information, we also larger level on image collected from a social media platform to do different application. One of the interesting application we have been done is utilize the image collected from social media for flood water depth detection and mapping. The idea of this work is we first segment, identify reference objects such as buildings, humans, vehicles, traffic signs, lamp posts, and then automatically identify the the proportion of object above and below the water to perform water depth detection and mapping. In addition to utilize the text and the image features separately, we also fuse text and image in our subsequent multimodal data fusion effort. In particular, through this model, given image along with text, we can automatically classify it into different categories of situational awareness. In particular, our tasks include three. The first one is first identify disaster relevant information. Second is we classify disaster relevant information into different categories, such as infrastructure, utility damage, rescue, volunteering, or donation, vehicle damage affected individuals. In the third task, if the image is related to infrastructure and the utility damage or vehicle damage, we further classify it into different damage level, like no damage or minor damage in totally destroyed. Then the next effort we made is the self-supervised learning framework based on the transfer learning, where we based on large-scale pre-trained foundational model to automatically to perform the task of real-time classification of disaster image. Based on the model evaluation, our model can achieve reasonable performance around 80% of accuracy. Well, based on my research in the last couple of years, we can see like several advancement development in this field can be categorized, described from data methodology application. Since I'm running out of time, I will not introduce them detail, but basically at the data perspective, we start from small official data sources, statistical information to large scale crowdsourcing dynamic big sensor data sets. Methodology-wise, we start from a manual feature extraction to machine learning to recent deep learning, supervised learning to self-supervised weekly supervised learning, single model data integration such as image or text information to multi-modal learning integrate both, for example, text and image feature to multi-source, multi-modal data fusion. From traditional simple machine learning and AI model to GeoAI, in future we will expect more explainable, interpretable, transferable, even physical informed GeoAI model will be developed to support high resolution, real-time, global, large-scale mapping with the innovative methodology and the big data sensor. Well, I will stop here. If there is any question, happy to answer.
Okay, thank you, Dr. Huang. Do we have questions online or questions in the room? Anyone here? Any online? No one this time? Anyone in the room? No, I have a general one. So it seems like there's so many models being developed on the GeoAI side of things. This is such an active research area. Is the research committee and popular software vendors, are they working together, I guess, to integrate some of this stuff into the tools we use in our daily lives? Or is that kind of a separate process between the things you develop and other researchers and what we see as availability in our geoprocessing tools?
Yes, this is really and yeah, we do witness several efforts on the open science and the open source community. For example, GitHub, and especially if you use the manuscript, and you will see all the journals encourage you submit your source code and the data sets for your models, and I see that. Eventually, there are more and more open source will be available. But I think that there is still lack of initiative, for example, for different domain, for example, in the natural hazard domains, and there is targeted effort should be leveraged to collect all relevant training data sets as well as the models for users to easily find the relevant information and the sources. And we do witness for each effort. We start with the search relevant information data source, and I often find, and also my students find, it's really time consuming to identify relevant information. But if there is such an open community, can do make an effort to make a sources and the open available and easy searchable, that's really would contribute to the science community.
Okay, thank you. Any questions? We got none online or none in the room? Okay, thank you very much, Qunying. Join me in thanking her. We really appreciate it.
Enjoy class day.
Yes, take good care. So we're at the point in our program for folks online. We're going to be taking a break until 1 o'clock Pacific time. So we have about an hour and what is it? An hour and 10 minutes. Folks in the room, we have pizza either almost here or just about here. So stick around, take a short break. We'll have a little over an hour to get some food and talk and discuss before we come back for a series of short talks and an additional invited speaker.